this is an exercise for you. Don't have time to actually go through it right now, but I would encourage you to spend time and maybe you can formulate that. You can always find me. I'm going to be here the whole week, and let me know if you want to discuss your formulation. Okay. So one more thing I want to discuss about is, I mean, there are many different ways to formulate an optimization problem. You can use many different software. I have here MATLAB. What I want to discuss is the nodal prices, that I'm not going to go too much into that, but nodal prices are fundamental for the operation of the market, right? And so I guess some of you have already programmed. Oh, I'm sorry, yeah. I guess some of you have already implemented DC-OPF, so how do I calculate the nodal price? No, wait. Thank you. Somebody else. How do I calculate the nodal price? Yeah. Oops, sorry.
The dual of the
dual?
Yeah, the dual of the balance, the node balance equation in that node, evaluated in that node.
So exactly, it's a dual variable, which we also call it Lagrangian multiplier. So what happens is that the solvers usually, so when they solve it internally, they have to calculate the dual variables or the Lagrangian multipliers. Okay. So it is an output of the solver. And I have here just the limprog in MATLAB. You can find here that you can ask for lambda. Lambda is this Lagrangian multiplier. You have to identify that you want the lambda of the nodal balance equations, so my equality constraints. So the Lagrangian I have one Lagrangian multiplier for every constraint, equality or inequality. If I can find, so I have to identify that I want the lambdas of my equality constraints that correspond to the nodal balance equations. And then I get one price, or actually one value for each of those constraints. And this is my nodal price. Is that clear? I know we are actually somewhere here, and actually if you put it in your MATLAB code or wherever you put it, you're going to figure that out, but we don't have time to do that now. Still, I mean, in your projects, you might need to calculate that in some of them. Okay? Good. Discussion points. So I also had a discussion during the break. I have presented here a formulation that I think is it's kind of clean. Because when I talk about deltas, for me, these are the approximation of the voltage angles, okay? I have a DC-OPF where deltas is just a variable, and if delta is just a variable, is not expressed in radians, then I don't need a per unit. But if I the way that we have actually approximated the power flow problem is that delta is my voltage angle and must be expressed in radians. And if that's that, then P must be in per unit. And I think it's better if you make the effort to do that, because then everything, let's say, is consistent. Otherwise, delta has no meaning at all. Good. Then we talked a bit about the admittance matrix. The susceptance is the one over the reactance. And what is, we said that about the diagonals and off diagonals. What is important for me here is that if you take the complex value, so if I take the ohmic resistance R here plus Jx, and I invert that as a complex number, I'm going to get a minus here. And that's OK. So people that actually implement both DC and HOPF, they sometimes get confused. Because here, when I do the DC-OPF, I don't have a minus, and I only have to invert the real value, and the minus, the minus comes actually from inverting the j. Okay? And we don't have that there. So it's very important that when you do DC-OPF, you just have 1 over xij. When you do AC-OPF, you invert the whole part here, and there's going to be a minus here, and you must make sure that there is there. Otherwise, your formulation is not going to be correct. You cannot take the imaginary of your admittance matrix for the AC-OPF and say that, you know what, this is my bus acceptance matrix. No, it's not. Shall I say that again?
Yes, please.
Great. So what happens is that, let me so I have my line, right? My line is an impedance. It's Rij, Zij, plus J Xij. That's originally how it is, the series impedance. Okay. If I get the admittance of that, my Yij is going to be my conductance Gij plus J Bij. Okay, I just invert that. This is 1 over Rij plus Jxij. If I go to the AC-OPF, I have to build my bus admittance matrix of my Ij. What we said is my Bij, my B bus admittance matrix here is going to have like B11, B12, B13, right? Or and yeah, let me. These are not the same. So this is yeah. Let me put that B12 plus B13. My B12 here is not the imaginary part of that. So B12 is not the imaginary part of Y12. The difference is a minus, but this minus can be fundamental or crucial. So if I go for the DC-OPF approach, my B12 is 1 over X12 and end of story. Clear? Okay. And this is just a tip. If your DC-OPF does not converge, the first thing you usually do is check your admittance matrix. I mean, or your constraints, but often the admittance matrix, something's wrong there. Okay. So I'm going back to the nodal prices because I think this is very important. People think that if I take the Lagrangian multipliers of my optimization of the node balance equations, then these are prices. These are prices only if the objective function is minimization of costs. Okay. So to get the nodal prices, I have to have an optimization that minimizes my costs, not losses, not the angle difference. It must also not be multi-objective. I have to minimize my active power costs. And that's my objective function. And the reason why is that if you actually sit down and derive the Lagrangian, you're going to see how you actually derive the Lagrangian multipliers. And you're going to see that this sensitivity is like the sensitivity of cost over pi. Okay. So one thing is that, yeah, you have to make sure that is a minimization of active power costs. And then the Lagrangian multipliers of the nodal balance equations, they represent nodal prices. And I just have this because I don't have time to go through that. because we can formulate the DC-OPF also without the angles, which for us is just a help variable. We can actually eliminate those with a simple reformulation, and we have these sensitivities that we call power transfer distribution factors. This is just, let's say, the result of a matrix multiplication and an inversion. Okay, but the thing is that these PDTFs are just linear sensitivities that what they do is they relate the injection of power with a line flow. So what they say is that here this can be 0.6, let's say, for this node. This means that 60% of whatever goes through here goes through that line, and 40% goes through here, for example, to reach somewhere. These are linear sensitivities. I won't go into much more detail. I have a reference if you want. I have it here because the zonal pricing system in Europe, they use these factors. Okay, and that's the formulation that they use for the market clearing, based on PDTFs.
Spyros.
Yes.
I missed the point. The zonal market pricing in Europe are using what?
So we have this internal European market, is the Central West European region for the moment. What happens is that every country is a node. So you can think of a power system, every country is a node, and we have the interconnections. So one line that connects every country, these are the lines of my system, right? So I solve a DC-OPF with about, I don't know, 10, 15 nodes, how many countries there are right now in the European integrated European market. And there we have one line for every country, inter-country interconnection. Okay. So this has an aggregated limit. So for example, Germany and Denmark has maybe, I think, 4 or 5 different lines, AC and DC. They aggregate them all together, and they take the sum of their capacities. It's not going to be exactly the sum. You have to subtract a lot of that capacity because you have security constraints, you have maybe other issues, but it's going to be some capacity between these two countries. And then, because most of these connections are AC, this is not true for Denmark and Germany, but Germany and Netherlands if you want. So then you have to have some kind of reactance, right? An equivalent reactance between the two countries because the power is going to flow following the minimum reactance. The minimum resistance path for DC-OPF, this is the reactance. So instead of having the reactance, they have these PDTF factors. Okay, and these factors are fictitious, but they are based on the physical flows. These factors take into account, besides the physical flows, also the N-1 security criterion and other issues. But it's a fictitious number that they use for their markets, and something that has been coordinated all over the European operators. Questions? Yeah. Yeah.
Yeah. Philosophically, would it make sense to introduce a constraint if we have our voltage angles that says that these angles need to be smaller equal to a certain value to ensure that our linearization is not too bad?
Philosophically, yes. But you wouldn't do that. I mean, you accept that this is a linearization and you use it. The reason to include the voltage angles in the objective function, to minimize the difference, right? Not a limit, but you can include it in the objective function to minimize the difference. There are some formulations because sometimes your objective function is very flat. This means that there are many solutions that have exactly the same cost, so the optimization does not know what to pick, or picks one of them randomly. And then you might want to drive your optimization to one of those solutions that also has a minimum angle difference, because in that case, you also minimize the flows, and then you minimize the losses on the line. But this is a multi-objective optimization, since you have 2 different objectives, and you must be very careful how you define the weights. Because you can actually, if you put a large weight on the voltage angles, then you don't get to the minimum cost solution, right? Okay. But putting a limit on the angles, in the DC-OPF, you usually don't do it. In the AC OPF, you do it because every 360 degrees, you have exactly the same voltage, right? So you put a limit so the optimization can look into 0 to 360. Clear? Yeah. Okay. Other questions? Okay, so I included, let's say, a short break so that it will help me introduce better the topic of the next lecture and also what Pascal is going to talk a bit tomorrow. So the DC-OPF is a linear program. It's a linear program because we have a linear objective function and all our constraints are linear. The AC OPF is not linear. And on top of that is also not convex. Okay. So why have there been efforts to convexify the problem? A convex problem, and this is actually a convex function here, has one global minimum. Okay. And there has been a lot of efforts or a lot of work on convex optimization, how can actually solve this problem efficiently. And to be honest, actually, there are guarantees that we're going to converge usually to a solution, and this is going to be also the global optimum. In the non-convex problem, there is no guarantee, first, that we're going to find a global optimum. And there are also no guarantees that we're going to, sometimes we don't even converge to a solution. Okay. So why do we want to convexify that? So why is it so important for us to find the global optimum? Okay. So let's suppose we have the optimal power flow problem, and our local solution that might be here, for example, right? So we converge maybe to that solution while this is the global one. And this might have a difference maybe of 1%. 1% in the power systems can be actually quite substantial. Okay. The US electricity industry is, has an estimated cost of about $400 billion a year. Improving that by 1% is $4 billion a year. Okay. It's worth the effort, to be honest. Of course, I mean, convex relaxations have now been, are now under development. They also have their weaknesses, but the main motivation is to find a way to identify the global optimum of our original AC OPF problem, and to make sure that this is the optimum. Okay. So there are two reasons that we're actually looking at that. First is exactly because we really want to achieve that global optimum. The second reason is that even if we don't really find the global optimum, or we cannot really get there, we know what's the distance from that. So the convex relaxation is going to give us a lower bound that can tell us that then our nonlinear program can, we can actually measure how far away we are from the absolute best. Okay. Is that clear? Two reasons why we're looking at the convex relaxations, among others, of course, but it's also a very interesting problem from a mathematical perspective, to be honest. So there have been many different approaches. Pascal has also proposed one, and is going to talk about that tomorrow. What we are going to do in the next lecture is going to be one of the first. To be honest, is not the first, but it has gained more traction maybe in the last years. The SDP formulation from proposed by Chatzivasileiadis and Timelo. Okay. And what we're trying to do actually is we have this non-convex problem, right? And the convex relaxation is actually trying to put an envelope around that, so relax the problem, but in a way that the global optimum of the relaxed problem coincides with the global optimum of the original problem. And the main, so one thing is to relax the problem, but the main challenge is to find a relaxation that is actually exact. And by exact, we mean that the global optimum of the relaxed problem is the same as the global optimum of the nonlinear original problem.
Spyros?
Yes?
Sorry, but we don't need to carve the local minimum, right?
No, it can also be somewhere here. This doesn't matter. I mean, what we're interested in is this one, that this must coincide. We don't care about it. This is, yeah, by coincidence. Questions? Okay. Yeah. So break is over. Let's go back to the AC OPF. So for hopefully, let's say the next 15 minutes, we can discuss about the AC OPF so that then we can have time and go into the convex relaxations. So AC OPF, minimize what? What can we minimize?
Cost.
Yes, costs. What else? Losses. What else? Emissions. Yeah, if we can model that, yeah. We are not going to have constraints now for that because we need to have the appropriate constraints. Yeah. Yes, voltage deviations. This is also part of the, let's say, fundamental AC OPF problem. Yes.
Could we say frequency issues? The
frequency is more a dynamic problem. You can approximate that if you want, but I'm pretty sure I can think of a formulation that can do that, but I wouldn't. We won't discuss it, and I wouldn't recommend it probably to go with frequency. So these are the three main things. Okay. We can so losses, costs, voltage deviations. One can also think of reactive power, maybe. Okay. And then we have the constraints. So we have the full AC power flow equations instead of the linearized ones that we had here, right? We have the line flow constraints. Generator now we have, so the difference with the DC-OPF is that we have active and reactive power, voltage magnitude, and voltage angles. Okay? And we have to have limits for each one of those. Because there is a limit on how much a generator can produce. There is a limit also in the reactive power that can actually inject or withdraw from the network. The same goes with the voltage magnitude. And as I said, for the voltage angles, it's not necessary, but it helps our optimization usually if we limit that between 0 and 360. This is a nonlinear problem. There are a lot of iterations, and we want to limit the feasible space to one area instead of actually jumping from 0 to 360 or 360 to 720 and things like that. Okay. Usually we limit that, either from minus pi to pi or from 0 to 2 times pi. It's up to you how you want to. What I also want to spend a little bit time on is the line flow constraints, because now we don't only have active power. Now have a freedom to select our line flow constraints. And this can be apparent power flow, active power flow, or current, because now we have voltage represented. We have the admittances, so we can actually calculate the current. What would you pick? Yeah. We have also the microphone.
I think I would go for the current if I want to capture the thermal limit of the line.
Right, yeah. So if we want to capture the thermal limit of any overhead line or cable is actually expressed in amperes. Because how much current flows through that cable is important so that the cable does not melt, right? So if we really want to go for the thermal limit, then we must have the constraints, the line flow constraints in current. When would we go to the other constraints? Yeah.
Maybe in some cases, like we actually have the line flows as explicit optimization variables. So in that case, it could be easier to restrict the active power flow or the reactive power flow on the line compared to restricting the current.
Yeah, so for example, if you want to keep the power constant or to maximize the power flow between two areas, that's what you mean?
Yeah, or I mean, just if actually the power on line is like an explicit optimization variable, like
How?
if we,
In what? So, do you have a problem in mind that it can be?
no, not specific problem, but
Okay.
I mean, I've seen formulations of optimal power flow, like specifically maybe relaxed versions when the line flow, like the active power on a line, is an optimization variable. So.
Yes, maybe. Yeah. Yeah. If maybe if you want to maximize the flow between two areas, but I cannot think of something else. Maybe there are other problems. Yeah. Yeah. Other ideas? Yes, Thomas. Just wait a minute. You can thread me.
Yeah. Maybe the apparent power flow for the sizing of transformers?
Yes, indeed. Very good. So what Thomas said is for the transformers, because the transformers are also branches, right? They are modeled similar to a line. It's just that for transformers, even in the AC power flow, we just have a series reactance. There, for the transformers, important is the rated power. And for that, we need the apparent power flow. Yeah?
Actually, question as well as a formulation maybe, but if you want to maintain the power quality, then you look at the difference in the ratio of the active and reactive power as well in that, and you can try to maximize the power quality as well.
So, yeah, in a sense, so the power factor, right? Yes, yes, yes. This can also be, yeah. But for the line flows, I'm not sure if you really need that for line flows. Because you want to maximize the power quality maybe in some load or maybe in some, yeah. Yeah, but yeah. So what I want to say here is that the line limits are divided in 3 parts. And this has to do with their line length. Okay, and let's talk about overhead lines now. So for short lines, the most important limit is the thermal limit. After a point that I don't want to mention now, I don't have exactly in mind how much this is, some kilometers, over 60 for sure, maybe even over 100. The thermal limit is no longer important, and then it's the voltage drop. Okay. And for long lines, the important is actually the stability limit. So if you have if you had already a course in power system fundamentals, then you know that there is a maximum transferable limit between 2 nodes. This becomes a limiting factor when we have long lines. Long lines, like what Miguel said, between northern part of Canada and down to Toronto and even down to New York, or northern part of Sweden down the southern part of Sweden. In general, long lines like 500-kilometer lines, their main limit is the stability limit, and this is expressed in active power. And in that case, we need the active power flow limits. Okay. So it needs some engineering judgment to understand or to pick which of those limits you really need. Yeah. Can you pass us the microphone? Yeah.
Yeah, why do I need to decide on this? Can I not implement all of the 3 constraints and then I know that, okay, some of them will not be binding, but I don't need to think about it myself?
You could, but if you start, your problem becomes more and more complex, and usually the main idea is to simplify as much as possible. To have only the necessary constraints, right?
Okay.
Yeah, you could, yeah.
So actually it depends on the type of network that you're working on, the level of voltage, right? For example, at distribution level is more important the line current limit, and at transmission level is the active power flow limit because of the reactive power doesn't travel to long distance. But what about the apparent powers? It's more for...
So I agree that maybe for distribution grids the line current is important, but the line current is also important for transmission grids as well. If you have lines shorter than, let's say, 60 to 100 kilometers, this is the limit that you really want. Okay. Active power is for stability limit. This is for very long lines. Okay. For apparent power, what we said, what actually Thomas mentioned, is it's very good for transformers. It's the appropriate limit to limit the transformer loading. Okay. Other questions? Yeah. Okay.
So what you're saying is the active powers only become significant when the line is long.
Yes.
And then when it's short, that would be the apparent power.
Apparent power or line current. To be honest, I prefer the line current formulation. It's the most accurate because this is the thermal limit. That's how it's expressed. And it's also linear in the AC OPF. It's admittance times voltage. Okay, I'm going on. Yeah.
Question about the structure of the network itself, because as a follow-up to a question which was asked by my colleague over there, is that in a transmission line you have more, the conductance plays a higher role than the resistance. But if you go towards distribution network, the resistance is much more important than the conductance.
You're talking about susceptance and conductance.
Sorry? Yeah. The
or reactance and resistance.
Yes.
Okay.
So just to think about the trade-off which is involved. So for some networks, if you're looking at the resistance or the impedance, then it's more important to consider as you said, the line limits. Whereas for the conductance of the transmission line, it's more important to consider the voltage limits to the reactive power control, right? Just to make sure I get that part right.
Can you repeat the question?
So for the transmission level,
yeah,
when you have the longer lines, the voltage control through reactive power is much more important. And for the distribution network, because there's a trade-off, right? You have the resistance, which is much more significant in the distribution network, so the thermal line losses are much more important that time.
Yes.
But when you move to the transmission level,
yes,
the reactive power management is much more important because the conductance value is higher. So you basically have capacitors which can provide you with the reactive power for stabilizing voltage.
Okay.
So in that sense, like can the line current limits be used for both, or is there a case where one of them is not an important constraint anymore?
So what I would say in that sense is that in the transmission system, the line flow limit is more important than the voltage limit, because usually you have ways to control your voltage. If you have a transmission system, each one of those nodes is actually a big substation. There is capacitive, let's say, reactive power support and voltage support in almost every substation, in some sense. In the distribution grid, we don't have this voltage support. Okay, so usually, but this is we cannot generalize, right? Is that in the transmission system, the line flow limits are the binding constraints. What's important for the distribution grid is the voltage drop. So the voltage is very crucial that it stays within the normal operating limits, because you cannot control voltage on every node on a distribution feeder. Okay, so that's the way, yeah. But you need both constraints. I would go with line current in both cases and the voltage constraints. But then you're going to see that usually other constraints become active in different systems. Okay, yeah. Okay. So what I'm going to do now is I'm going to show you how we formulate the AC OPF problem, and then I'm going to spend a bit of time in some parts of it. Okay. So first of all, the more straightforward parts. I mean, we have minimization of something. Here I have just the cost of the active power. Okay. I don't have reactive power because in the market usually, usually what counts is the active power. Okay. That's where we have the major production costs. And then we have the different constraints for our variables. So as we said, we have 4 different types of variables. All of them are optimization variables. Even if they are not expressed here, we have just zeros for the rest. So no costs, but they are optimization variables. So the active power limits, reactive power limits, voltage magnitude, and voltage angle. And since we have this kind of formulation, it's also clear that here we go with the polar coordinates. Okay. Because we're going to see that in the convex relaxations, we go with the rectangular coordinates of voltage. Here we have magnitude and angles. Later, we're going to have real and imaginary part of voltage. So what are we missing? Line flow constraints and nodal power balance. Okay. So line flow constraints. If we have line currents, then it's the line admittance matrix. I'm going to spend some time discussing about that. Times the voltage. This is Y times V, right? Admittance times voltage equals current, right? This must be less than the line limit. The thing is, in the AC power flow, if I go from I to J, it's a different power or different current than if I go from J to I. Okay. And I have to have both directions. And now, because we're talking about complex values here, and the limit is a real number, the limit is just the maximum current. I need to take the absolute value of that to get the absolute value of the complex number. Clear? If I go to the apparent power, I need to multiply that part with a V from the left. Because it's YV square if you want. In a matrix expression, we must be really careful the way that we actually put the different vectors and matrices next to each other. And then we have the nodal balance equations. I mean, Miguel showed that with sine and cosine. I'm showing that in a matrix form. To be honest, I very much like this form. It's very elegant. But besides MATLAB, I don't know if some other program can actually express that in matrices. Maybe Python, I'm not sure. But this expression here has all the nodal balance equations in one line. Okay. What's very important here is that this is the diagonal. It's a diagonal matrix. Okay. I mean, the voltages are in a diagonal, which actually creates a lot of problems because the diagonal operator is not. Okay, so having said that, what I want now to spend a little bit of time is what is this Y line that we call line admittance matrix, and what is this Y bus that we call bus admittance matrix. Okay. So as we said, the usual representation of a line, either cable or overhead line, is the pi model. For overhead lines, you can use this model from 25 kilometers up to 250 kilometers, and this is actually, it's a very good approximation up to 250 kilometers. Okay. Length of line. So what we do here is we have the series impedance, and we have two shunt capacitances. I have to change that, I mean, I have to calculate my admittance here and my shunt admittance. And then I got the current, right? And my current, what flows in here is the sum of, so what comes in here is the sum of what flows on this line and what flows on here. And what the current that flows on the shunt element is going to be the voltage here, VI, times this. And this is what I have here. The current that flows on that branch is going to be the voltage difference, VI minus VJ, times the admittance here. And I hope that this is straightforward for most of you. So then this is the equation of what flows from I to J. So my current from I to J is this. Then I do again the regrouping, as I did, and I formulate a matrix that's actually one element is the shunt plus the series reactance, the series admittances, and the other is the minus of the admittance. So it's very similar to this one. The difference is that here in the diagonal, if you want, I'm not going to have only the sum of all branches, but also the shunts. And I have that in the slides. You can go through them. Whenever you try to implement an AC OPF, you can look at the slides also to textbooks and see how this is. What I want to say here is that from J to I, so this part is the same, exactly, with a minus, but it's the same. What's not the same is this part here. This is y sunt j times vj, and this is y sunt I vi. And that's the reason I have different I flowing from I to j and j to I. And you must be really careful. Because if you only model one direction, you might not get the full other I mean, the other direction might be constraining, and you don't really realize that. I won't go more into detail in that because I want to move on. And then I have the bus admittance matrix. What I want you to remember here is that apparent power is equal voltage times the conjugate of current. That's for three-phase power. Or, yeah, the AC power. And the way that we actually formulate the bus admittance matrix is very similar to what we did in the DC-OPF. As I said, the difference is that here we have the admittances instead of the susceptances, so minus admittance in every case. And in the diagonal, we have the sum of all the admittance of all branches plus the shunts that are connected to that node. Yes. Can you?
Just a very quick question.
Yeah.
So this expression of the apparent power, it's in general for AC.
Yes,
right?
general for AC.
Doesn't have to be free phase.
No,
or
no,
one
no.
phase.
It was a slip-up. Yeah. General for AC. How we build that, you can also read that in the. Sorry, guys. I don't think that we need to go into more detail here in those. I have some further reading if you want to take a look at different parts. And this is the wrap-up that maybe you can stay a bit here. So the DC-OPF is used at the moment in most market clearing algorithms. They are a version of a DC-OPF. From my knowledge, the only market I've heard that they might go, or they are going a bit towards AC OPF, is the ISO New England, that they are trying to build an AC OPF market clearing tool. But the future, or what many people think the future is going to be, is that we want at some point to move to an AC OPF formulation, both for market clearing and operation. Okay. So that's our job, actually, to develop a good tool. So the good thing with DC-OPF is convex and can solve fast and can solve for very large problems. I mean, if you go and solve thousands of buses with DC-OPF, probably you're going to find a solution. With AC-OPF, I've tried in my laptop, let's say, beyond 9 to 10,000 buses, it doesn't convert. Okay. But I mean, of course, this depends on the solver, this depends on the problem. There are many different. The problem with DC-OPF is only active power flow, and it doesn't have any, doesn't include losses and voltage limits. The AC OPF can actually model many different things, so we don't need only to optimize costs. We can optimize voltage limits or voltage profiles or line losses. But it's not convex, so there's no guarantee that we find the global optimum, and it can be, it is computationally expensive, it can be intractable. Okay, we might not be able to find a solution. Questions? Yeah.
Just a wrap-up question on my side. It's written also on the slide. What makes the DC-OPF suitable for transmission networks, not for DC or for distribution networks, or the other way around? What makes the AC-OPF suitable for DC and maybe not for AC?
What makes the DC-OPF?
Yes, what makes the DC-OPF suitable for transmission networks but not for distribution ones?
So the assumptions that we have made in order to linearize the AC power flow are the following. First, that the ohmic resistance in the lines is much smaller than the reactance. So R much smaller than X. This is one assumption that it is true in transmission systems. It's like R may be 10 times smaller than X, but in distribution is not like that. Second, we assume constant voltage equal to amp per unit. And we assume that because we assume that every node in the transmission system is controlled in terms of voltage, so it can keep a constant voltage. And this is also not true in distribution systems. Okay. So these are the two main things that, yeah, it's not a good approximation for distribution. Or not as good, let's put it as like that. It's not as good approximation for distribution.
What happens about the Euphemia day-ahead market algorithm? Is DC or AC?
It's DC.
DC.
Yeah. Other questions? Okay. So by that, we conclude this part, but we still have some time left, 15 minutes, and I want to go into the convex relaxations. So I'm sorry for not letting you enough time to relax, but if in 15 minutes you can have a coffee break, okay? I have also, in the slides are uploaded, there is also an appendix how you go from AC to DC power flow. I'm not going to go into that. You can take a look at it. And yeah, if you have any questions, we can discuss.
Spyros.
Yeah.
One not hypothetical, but a helpful question. Linear algebra is linear algebra more important in this issue to be known by us, or differential equations? What type of mathematics?
For optimization or for this kind?
For ACDC.
Linear algebra is, yeah, linear algebra is number one. Mm-hmm. You need differential equations if you go deep into the Karosh-Kontager conditions. Okay, but this is what the solver does. To be honest, I think it's very beneficial to know about that. But to formulate a problem, linear algebra is what is necessary for this kind of problems. Yeah. Ready for the convex relaxations? Yeah.
If we want to model,
can you?
If we want to model a network with transformers, converters, and storage, what kind of modeling do you propose? Do you think it's best suited?
Depends on your problem, to be honest. I cannot, it really depends what you really want to do. If you have storage, you must have time coupling. So it must be multi-period OPF, either AC or DC, it's up to you, yeah. But, and then depends what kind, yeah.
And transformer with tap changers?
If you have tap changers, then you need voltage. So you need to model voltage, and then you have to go for AC OPF, or let's say that AC OPF would be a better suited.
Okay. Thanks.
You can even approximate that, right? I mean, there are also formulations in between. There is a vast literature on every possible type of OPF you can find. There are different ways, but these are the two main, let's say, the two main points where somewhere in between you can move. I'm going on. Okay, so what I'm going to focus in this lecture is the SDP formulation for the convex relaxations of the OPF problem. Okay. We're going to hear much more about that tomorrow. Not about SDP, but in general about convex relaxation. But what I want to do in this lecture, I mean, if you go through the math, I don't have the time within 1.5 hours, or even less than that right now, to go through the exact math. But what I find very important here is to give you an idea why SDP. So what is SDP? Okay, and we have defined a project on the convex relaxations for the AC OPF based on SDP that you can actually take, and you can go through the implementation and see the different issues that we're going to discuss. But what's important for me here is to give you the idea, or what is SDP, what we're doing there, and then how we formulate the problem. Okay. Feel free to interrupt. This is something that I saw before. I'm not going to say that again. I'm going directly to what is SDP, right? So how many of you have an idea of what SDP is. So who can explain to us what is SDP? So who has worked with SDP? Yeah. Do you have the, yeah.
Really?
Okay. Basically, it's an optimization problem in which you can have inequality constraints that can be defined relative to a cone. And for example, you can say that a matrix should be semi-definite positive. So that's what it stands for, semi-definite programming. Yeah.
Yeah.
No, I just wanted to say the same, that
Okay.
semi-definite matrices are basically matrices that guarantee that when you pre and post multiply them by a vector, it will be positive. And they define conic subspaces, and they have some nice properties as you've shown with convex function, but just in multi-dimensional spaces.
Nice. Any other comments? Okay, let's go and see a bit what why SDP. So why do we want to go into SDP, right? Because we have linear program, we have quadratic program, we even have non-linear programming. So why do we need something more? Okay. So Bob Freund from MIT actually has this kind of quote in his lecture notes. Semi-definite programming is the most exciting development in mathematical programming in the 90s. Okay. So this happened in the OR field around in the 90s. It came into power systems about 2008. We had the first formulation. Okay. It took a bit of time, but we got there. So what I have here is I compared the LP that I hope all of you or most of you are familiar with how we formulate the basic or the standard formulation for an LP, linear program, versus the SDP. Okay. To be honest, they are very, very similar. And to be more exact, the SDP or the LP is a special form of SDP. Or if you want, the SDP includes LP in it. Okay. So both problems have linear objective functions. Both problems have linear constraints. The only difference is that our optimization variables in the LP must be strictly non-negative, while in the LP we organize them in a matrix that must be positive semi-definite. That's the main difference. Okay. So in the semi-definite programming, we organize our optimization variables in matrices or in a matrix, and this must be positive semi-definite. Okay. So maybe not all of you know or remember what a positive semi-definite matrix is, but we're going to look at it a bit in a couple of slides. First, I want to go into, before going into the last constraint here, I want to actually spend some time in the other constraints. This bullet here actually means element-wise multiplication. Okay. So imagine now that instead of having an optimization vector, right? So we have a vector of optimization variables as we have in a linear program. We now have a matrix that we optimize over. So we have this matrix, and what the way that we formulate the SDP is that we have element-wise multiplication. So then our costs are also formulated in this kind of way. So what happens here, what I want to say is actually that, see, it's just a linear cost function with linear constraints, with the difference is now that instead of having so in an LP problem, x11 must be positive, x12 must be positive, x21 must be positive or non-negative, to be non-negative, and x22 must be non-negative. In the SDP, this matrix now must be positive semi-definite. Great. So I will skip that. You can you can formulate the problem, and then you can find the solution there. So now we need actually to understand better what is a positive semi-definite matrix. So what is a positive? We heard already that if we pre and post multiply with a non-zero vector, right, the result must be non-negative, right? What's that?
Also with zero, because it will be zero.
Yeah, but I mean the idea is actually that we. What are other properties of the positive semi-definite matrix? Yeah. What's that? Yes. All eigenvalues must be non-negative, right? Yeah. Other?
They're also decomposable. There is a nice Kaletsky decomposition for a semi-definite matrix always.
Yes. True. Very nice. One thing is that the positive semi-definite matrix must be symmetric. Okay. So the first thing you check is if your matrix is symmetric, and then you can start thinking about the rest. And then it's exactly what you said. So if we multiply with any non-zero vector, the result must be positive. The problem is that it's very difficult for us to check for any non-zero vector. And that's why we have other criteria to check if a matrix is positive semi-definite or not. And one of them is that all eigenvalues must be non-negative. We heard also about the Kolesky decomposition. And another that I'm going to use actually just for the next couple of slides, and that's why I have it here, is that all leading principal minors must be non-negative. And I mean, if you go, I mean, you can even check Wikipedia. There's a list of criteria that can tell you when a matrix is positive and semi-definite. I have only these because this is the definition, and these are the two that I'm going to use in this lecture. Yeah.
Explain what the leading principal minor is.
Yeah.
Cool.
So the leading principal minor, or the principal minor, if you want, is the determinant of submatrices of a matrix P. Okay. And you can divide that by order. So if we have a 2x2 matrix, what we do is we remove. So we take the first order principal minor, we remove one column and one row, so row 1 and column 1, and we get P22. Okay. The leading principal minor is when we always remove the last columns. So since it's only a 2x2 matrix, if we remove column 2 and row 2, we get P11. And this is the leading principal minor here, which is also in bold. So by definition, for a 2x2 matrix, when is this positive semi-definite? So the definition says that all leading principal minors must be non-negative. So when is this matrix positive semi-definite? I mean, you see that that is actually, so let's suppose that it is symmetric, right? P12 is equal to P21. It is symmetric. When is this positive semi-definite? Yeah?
P11 is non-negative.
Yes. And the determinant is not, yeah, the determinant and the determinant of the 2x2 matrix is non-negative. So we have two conditions that have to hold besides them being symmetric. P11 must be non-negative. The determinant of the whole matrix, because we had only 2x2, must be non-negative. 3x3, a little bit more general. I first have the third order, right? It's my whole matrix because it's 3x3. And then I remove one column and one row. If I want to get the leading one, the leading principal minor, I must remove the last column and the last row. So that's what I'm left with, right? And this one here. That's the leading principal minor, the second order. And if I want the first order, I remove 2 columns and 2 rows, and I'm left with P11. So when is this matrix P now positive semi-definite? Assuming it is symmetric. I promise a break after that. No. When is this positive semi-definite? No, you said for the to do. I want somebody else. What is not clear? So, I mean, for the people that cannot reply, what is not clear? What shall I say again? If you don't help me, yeah. Yeah. Guys, if you don't ask, I don't understand. Yeah, please.
I think P11 has to be positive, and also like that second order matrix like this P11, P12, P21, P2 determinant of that one has to be positive, and the third order one should be also positive determinant.
Right. That's correct.
Could be non-negative.
Non-negative, yeah, non-negative. Yes. So what we heard is that the three. So in the 3x3 matrix, we have 3 principal minors. Okay. The first one always is the matrix itself. So we have to calculate the determinant of that matrix, and if this is positive, then we go on, or non-negative. So if this is non-negative, then we go on and we find the second order. And the second order is when we remove one line and one column. And for the leading one, we need to remove the last column and the last row, okay? And we get this one. And then we check this determinant. Is this positive or non-negative? If it is, then we go on. And then we remove one more column and one more row. And then we're left with P11. And is that positive or non-negative? If that's as well, then we have found, or we can say that our matrix is positive semi-definite. Please.
Because it's positive definite.
Yeah.
Is there an advantage in that?
Is there an
advantage in having something that's positive definite against something that's positive
so
definite?
For the SDP programming, semi-definite programming, we don't have hard constraints because it's a hard constraint, right? It can go to the limit, but it's not. Yeah. There are cases, so for example, you can use semi-definite programming for stability, partial stability, and extract Lyapunov functions. And then the condition is that P must be strictly positive. And then there is an advantage. Okay. Yeah. Is this clear? Okay, then let's take a break until 4:20, and then we'll continue.